Hello, Riles. This is the first of 3 review lessons. I'm going to be going through the posted review examples, questions 1 through 4, talking about limits, first principles, derivatives, and implicit differentiation. So let's go all the way back to limits. The idea with a limit is most of the time we are given a limit in an indeterminate form, and we need to manipulate this format into an expression that would agree with the original expression for all values other than the value that x is approaching. And then we can use limit properties. And it's been a while since we've been asked to show all of those limit properties, and they were kind of intuitive, so we didn't ever really need to memorize them. Let's see, this expression here is an indeterminate form. As x approaches 2, the numerator approaches 0, the denominator approaches 0. That does not mean that the limit approaches 1 or infinity or that it doesn't exist. It means that I can't determine it in this form. It is indeterminate. When I factor the numerator, which is one of our key strategies, I notice there is a factor of x minus 2 in the numerator and denominator. Now just watch your brackets here. You want to make sure that you're taking the limit as x approaches 2 of x plus 2. It would be the same value if it didn't have the brackets, but it would mean something different. I guess if I'm using my limit properties, the first thing that I would do would be to apply the limit of a sum rule. So the argument here isn't that we make x 2. The argument is that it's much easier to see what happens as x gets close to 2. I couldn't tell here that as x gets close to 2, like when x is 2.01 and 2.001, that this expression is actually getting close to 4. But here I can tell that when x gets close to 2, this gets close to 2, so 2 plus 2, or something that gets close to 2 plus 2 is going to get close to 4. Okay, you are not making x equal 2. You are studying the behavior as x gets close to 2. Okay. Another indeterminate form here. Not a lot of students want to try factoring x as a difference of squares, so let's try multiplying by the conjugate of the numerator to kind of rationalize it. Let's squeeze that in there. Again, be careful with the brackets. Make sure that what you write is correct. In the numerator, I would like to expand because I would like to find some factors there. We'll do 2 times 2, that's 4. Plus 2 root 4 plus x minus 2 root 4 plus x is going to be 0 of those root 4 plus x's. And then I will have a subtraction of the quantity 4 plus x. All over in the denominator, I'm going to leave this factored because I hope I find a factor of x in the numerator so that I can divide out the factor of x from the denominator, which is causing problems for this limit. My numerator, 4 minus 4, is going to be 0, and then I have a subtraction of x. I'm not subtracting 4 and then adding x. I'm subtracting 4 and I'm subtracting x. Let's show the limit as x approaches 0 of. Now, let's show the factor of x in the numerator before we divide it. Let's show the expression in a determinate form before we use limit properties or use that sort of loose strategy of direct substitution. Okay, your goal is not to find the answer, your goal is to present a solution. And now my properties. As x approaches 0, this is now in a determinate form. I wasn't asked to show all of my properties, but I could say it's going to be the limit of a quotient, limit of a sum, limit of a power, limit of a sum. That gets close to 0, that gets close to 4, that gets close to 2, that gets close to 4, this gets close to -1/4. Okay. And then just for a bit of review of how we can manipulate expressions without working around with common denominators, let's try clearing our denominator. In both of these cases, we're multiplying by 1. I guess even over here, you're multiplying by 1. I'm multiplying by the reciprocal of x minus 2 in the numerator and denominator. Show it twice or 0 times. You're not multiplying by 3x. You're multiplying by 3x, 3x's. You could say as long as x isn't 0, but I'm interested in what's happening as x approaches 3, not what happens as x approaches 0. This will be the limit as x approaches 3 of the 3 divides by the 3. I'll be left with a factor of x. The x divides the x as long as x isn't 0. I'll be left with a factor of 3. Once again, I think I want to leave the denominator factored. Let's work with purpose. Do things on purpose. Make sure you know why you're doing things. This will leave me with a factor of 1 in the numerator and 3x in the denominator. This was one of our most common mistakes on the test, was students just writing 3x left in the numerator. And then as x approaches 3, limit of a quotient, limit of a product, or constant multiple, if you like, that gets close to 3, that gets close to 9, this gets close to 1/9, I believe. D, not a lot of students, actually a handful this semester, factored x minus 8 as a difference of cubes. I think the change of variable approach was much more popular though. So for change of variable, you find usually your lowest, your power that has the lowest exponent of x. And you upgrade that so that it is now your lowest exponent is going to be 1. Let u represent, what do I want it to be? Let's try the cubed root of x. I want to isolate for any other variable expression. That means that x would be u cubed. The other thing I need to do is communicate the change of the limit. And as x approaches 8, I'm actually taking a limit on here. As x approaches 8, the cubed root of x is going to approach 2. So you rewrite a new limit, a different limit that hopefully has the same value as the previous line. It agrees with the previous line. I'm always checking to see if these are in indeterminate form, of course, by the way. So this will give me u cubed minus 8 divided by 2 minus u. And the argument here is that I might find it a lot easier to notice that u cubed minus 8 is a difference of cubes and that it has a factor of u minus 2 or 2 minus u than just factoring in this format right here. And we use change of variable later in the course as well. Let's go u minus 2 multiplied by u squared plus 2u plus 4. Check with distribution. U cubed plus 2u squared minus 2u squared minus 8. And then in the denominator, I have a factor of 2 minus u. Where did I divide factors? Over here, when I divided identical factors, I was left with factors of 1. Here, when I divide opposite factors, I'll be left with a factor of -1. Once again, let's be very careful with our formatting here. This is not the limit as u approaches 2 of minus something or -1 times something. It is the limit of a product. So put those square brackets around there. You didn't need them when you had the quotient, but now that you don't have a quotient, they are required. Right. Now we are in a determinate form. As u approaches 2, that approaches 4, that approaches 4, that approaches 4. So this approaches 12, this approaches -12, if I've done that right. Okay. Last thing to watch out for, a question like this has thrown students for a couple of loops on multiple choice portions of exams. The most common incorrect answer here is that the limit doesn't exist because the student tried factoring and the student tried change of variable and they tried rationalizing and they tried multiplying by the reciprocal of x and nothing was working. Well, there's definitely a problem there if the student is trying all those strategies because the student doesn't realize that this is in a determinate form. As x approaches 2, this approaches 6, this approaches 1, that approaches 3. So there's the value of the limit. Right. First principles. If you're continuing with math post-secondary, and I hope you are, you'll come up with a more precise definition of a limit, and first principles are very useful there. So we're given the function h of x equals the reciprocal of the square root of x. We know our derivative properties now, so checking this answer should be pretty easy, but make sure that you get your marks for showing first principles. When we had exams, there was always at least one question that asked you to use first principles. And some of us used h as our change in an independent variable. Other students use delta x. I don't really care which one you're using, except for in this relationship, you shouldn't be talking about what happens as h approaches 0. So let's define h prime of x to be the limit as any other variable. Delta x works just fine. It's actually a more formal, maybe makes more sense than using h, because you really are looking at a change in x. Let's illustrate the idea of first principles as well here. kind of going back to advanced functions. We're trying to find the slope of the tangent. What we do is we set up a secant. Here's a comma f of a, and here's a plus delta x comma f of a plus delta x. Actually, we're trying to find the derivative of a function. So this would be x, f of x, x plus delta x, x plus delta x. There we go. We take the slope of that difference quotient, and then we study what happens as delta x approaches 0. As delta x approaches 0, the slopes of the secants will converge on the slope of the tangent. Okay, we can't make delta x equal to 0. We're studying the limit as delta x approaches 0 of h of x plus delta x minus h of x all over delta x. That's going to equal the limit as delta x approaches 0 of, let's go to specific equations here. This is going to be the reciprocal of the square root of x plus delta x minus the reciprocal of the square root of x all over delta x. And we get a bit of practice with limits. Review from question number 1, I suppose. I'm going to argue that we should get rid of the minor denominators first. Students that tried rationalizing first had a bit of a rough ride on a question like this on our test. Might have been this question. So I'm going to multiply by root x plus delta x over root x plus delta x. Again, I'm multiplying by 1. This will give me, let's see, definitely in an indeterminate form because I've set it up that way. But I just want to leave my denominator in a factored form. There we go. In my numerator, that factor will divide that factor, leaving me with a factor of root x. That factor will divide factor, leaving me with a root of minus 1 root x plus delta x. And now feels like a good time to rationalize. I'm still in an indeterminate form. As delta x approaches 0, that's going to be root x minus root x 0. And that's going to approach 0. So yeah, factors of 0 in the numerator and the denominator. Let's multiply by the conjugate of the numerator. Get some brackets in there. Root x plus delta x, root x plus delta x. Showing my work. All right, root x times root x. Let's get the notation first. Root x times root x is x. One of those minus one of those is going to be 0 of those. And then I am going to subtract an x plus delta x. All over. In the denominator, you know what? Let's just leave this factored. Root x plus delta x. Just need to make sure that we have all the proper symbols. Remember, we will be studying what happens as delta x approaches 0, and I can simplify all of this easier once delta x approaches 0. Limit as delta x approaches 0. Numerator is going to have a factor of the opposite of delta x. One more time. Actually, maybe 2 more times with the denominator. Root x. Sorry, let me squeeze it in here. Okay. Show your determinate form. You know what? I was thinking of maybe doing this one on the other side, and maybe I should have. Root x plus delta x. Root x plus root x plus delta x. Okay. And now I am in a determinate form. Let's see what happens as delta x approaches 0. My numerator remains constant at -1. Root x stays root x. Root x plus delta x approaches root x. Root x remains root x. Root x plus delta x approaches root x. Root x times root x is x. Root x plus root x is 2 root x. Hey, and we were just asked to find the derivative. It didn't say to simplify it in any way. This may not look like what our derivative rules will give us. There's some arguments to be made that you've got two factors of x here, so we should multiply them together. Well, you can make those arguments if you like, but I just don't see the need. I also don't see the need to rationalize the denominator. Sorry that it's a little bit squished, but it is going from top to bottom and left to right, which is all a teacher could ask for in a solution. That we don't start in the middle of the page and then have to squiggle around and have to ask for 3 extra pieces of paper. Right? Question 3. Maybe some of you will become TAs and you will have to mark. I hope so. I think a lot of you will make really good TAs. That wasn't, I hope you'll have to mark. No. I hope students are lucky enough to get some of you as TAs. Okay, in question 3, we are asked to find the value of f prime of -1. The point here is I want to review a couple of our derivative rules, but also I want to review when we should do algebra and when we shouldn't. And this is a time for arithmetic, not algebra. All we want to do is find f prime of -1. Let's substitute in as soon as possible, but not before. This is kind of like our related rates questions. Some of you are substituting in constant information too soon, or you weren't communicating when you were substituting in the instant. You can't substitute in -1 yet, because then you just get a constant value, and you can't take the derivative of a value. You can take the derivative of a function. Now, so we differentiate first. What have we got here? A quotient. So let's use the quotient rule. We were using the quotient rule still with exponentials, and it seemed to be going okay. We have a derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So there's a common factor of 2x. I could distribute, I could expand this. I could do all of that. I shouldn't do any of that. I should substitute now. I want to find f prime of -1. F prime of -1 is going to be 2 times -1 multiplied by the square of -1 plus 3 minus 2 times -1 multiplied by the square of -1 minus 3 all over the square of -1 plus 3 squared. Look at all those brackets. Let's also make sure that we're announcing what it is that we're doing here. What have we got here? -2. Let me start from on the inside. 1, 4, 8, -8. I don't know if I'm going to take it any further than that. 1, -2, +4, -4. Let me check that again. 2 times, that's 1, -2. Yeah, -4, I think. 1 plus 4, 16. What's that? -12/16, -3/4. Cool. We have seen questions where we were expected to manipulate algebraically. Again, this is not one of them. I'm not going to try to squeeze it. It's so tempting to use that space there. No, not for a product rule where I have to write a lot to the left and to the right. F of x equals square root of x minus 3 times x squared plus 4x minus 6. Biggest issue with the product rule is our use of brackets and just having factors of -1 without brackets surrounding it. Let's see, let's do the derivative of the outside here. 3 minus x to the exponent -1/2 multiplied by the derivative of the inside. I guess we have a bit of a chain rule here as well. Multiplied by the second. Plus, I'll do the first multiplied by the derivative of the second, derivative of a sum, like that. And we could go looking for common factors. We could reciprocate that. We could try to rationalize it, or we could substitute right now. I think I might do some manipulation and some tidying up on this step. For example, I think that I will just have a factor of negative, and then that's going to be -1 squared plus 4 times -1 minus 6 in my numerator. In my denominator, I'll have 2 times the square root of 3 minus -1. And then I'll have plus the square root of 3 minus -1 multiplied by 2 times -1 plus 4. As far as the amount of work to show, especially in a situation where we're doing distance learning, just convince me that you haven't typed it into the computer. We need to show the work. Let's see. We get 1 minus 4, that's -3, minus 9, or minus 6, that's -9, times -1 is +9. Try that again. -6 minus 4, -10, plus 1, -9, 9. Okay. 3, 4, square root of 4 is 2, times 2 is 4. 3 minus -1 is 4, square root of 4 is 2. And -2 plus 4 is 2. So I get 9/4 plus, that's 4 or 16/4. What's that, 25/4? Hope so. Okay. And question 4. Again, I think you're going to notice that our unit on exponentials was a culminating unit in a lot of ways, because we used quotient rules and product rules. We did some curve sketching and trig and exponentials, and we used implicit differentiation as well. If we have x squared plus 2xy plus 3y squared equaling 27, just show your step here when you're differentiating. Show your reader, even if you're just writing it out on the original line, show your reader that you are choosing to take the derivative of both sides with respect to x, because getting this notation right was a challenge, and I want to see that you're able to do that. On the left-hand side, I'm going to do the derivative of a sum. That'll be the sum of the derivatives. Derivative of 2x with respect to x is 2x. You could do times dx by dx if you like, but it's not necessary. I can't remember, I think it turns out to be faster if you treat the first as 2x and the second as y, but maybe I'm not interested in fast. Maybe I'm interested in safe. I'm going to use constant multiple, and then I'll do product rule. Derivative of x with respect to x is 1 times the second plus the first times the derivative of the second with respect to x. That's the derivative of y with respect to y. That's 1 times the derivative of y with respect to x. This was the weird thing about implicit differentiation for some students that just kind of memorized that this symbol is showing up, is you're asked to find dy by dx and you kind of discover it in the middle of your expression. If you want a review of a bit of a chain rule here, we're saying the derivative with respect to x of 3y squared is the derivative with respect to, here, let's set up our chain. 3y squared, I need a variable to link 3y squared to x. Let's use y. And then the derivative of 3y squared with respect to y is 6y dy by dx. The derivative of 3 times something squared with respect to something is 6 times something to the exponent 1, but then I have to multiply by the derivative of something with respect to x. Where did my constant multiple of 2 stop? I think it was back here. And the derivative of a constant is 0. Other types of constants include pi and ln of pi and e. Yeah. Okay, our goal is to find, I think usually our directions were find a simplified isolated expression for dy by dx. Let's see, let's divide both sides by 2 first. X plus y plus x dy by dx plus 3y dy by dx equals 0. Sorry, it should be deltas the entire time. I took all the time to go back and replace all of my d's with deltas. I should be saying them properly. I think I replaced them all. Let's subtract x and subtract y from both sides. and remove a common factor of delta y by delta x on the left-hand side. And then let's divide both sides by x plus 3y. Once again, showing your work. It's not convincing to see a solution jump from here to here. Okay, even if, sorry, there you go, to there. Even if you can do it in your head, that's never been our goal. Our goal has been to present a well-communicated solution. And that's hopefully what's going to happen in post-secondary. I know I had some calculus exams that were, or sorry, midterms that were 10 multiple choice questions, 10 marks each, and it's out of 100. It didn't go well. I think the open response calculus exams went much better, where I had an opportunity to show my work. We will continue next day with questions 5, 6, and 7 if you want to get ahead and compare your solutions.